Hello, we are Team OptiVAD. I am Justin Roderick. I was the project manager and I also worked on DevOps.
I'm Naomi Yoon. I'm the product owner and I worked on the API.
I'm Ashlyn Zimmer, and I worked on the front end and the UI.
I'm Cole Schmielars, and I worked on the front end and database.
I'm Aswanching Lissetti, and I worked on the segmentation.
And I'm Sylvia Rana. I worked on front end and 3D modeling.
So, what is a left ventricular assist device? The LVAD is a mechanical pump that helps the heart circulate blood in patients with severe heart failure. It is typically used as a temporary fix as patients get ready for transplant, but there are cases where it can be long term. A large risk associated with these devices is blood clots, which can often lead to stroke. This is what our software aims to help and decrease. We are trying to automize and optimize the placement of the cannula to get the best flow results and clot results. So the goal is to create an automated workflow where patient imaging data is processed without manual intervention. Research has shown that the angle and placement of the LVAD inflow cannula can influence blood flow patterns, and this is what our software will work on. Studies have reported up to 50% variation in clot rates based on how the cannula is implanted. So obviously, we want the implant that minimizes the clot rate.
So OptiVAD is a web app that helps Orlando Health physicians with performing these LVAD implants by generating a unique 3D model from CT and MRI scans of a patient's anatomy. OptiVAD is designed to require no special training so that it is as easy to use as possible for these physicians. The final model that we are aiming for is an accurate reconstruction of the patient's aorta with a cannula from the LVAD implanted, and this model will be used with the fluid simulation to minimize the risk of stroke for patients. So these were the project goals. First, we wanted to collect a patient's data through the project's interface. Then we would process the 2D medical images to generate a 3D model of that aorta. Then we would take the final model that we generate and run it through Dr. Kasab's algorithm to output a suggested placement for that LVAD. And of course, the overall goal was for physicians to easily access this process at every stage. And just as a quick note, we were not able to gain the proper clearance to directly access Dr. Kasab's algorithm, so it will not be integrated directly into the project. So for more specific implementation and for the scope of our project, we first retrieve the CT and MRI scans from an existing database. Then the physician inputs the patient's hemodynamic data into the project. Once we have all that data, we allow the physician to preview those images and select the ones that they want to use for the model. Then we use a segmentation model that is AI driven to generate a 3D model of the anatomy. Then we allow the physician to place a cannula onto that aorta as desired. Then that final model is saved so that it can be used in the simulation.
So this is kind of a high-level system design of the project. The most important thing to note here is that our backend is completely containerized and is hosted on AWS. That means we only need one connection to the backend from the front-end web app, and then all the containers can communicate within each other securely as they are all hosted within a virtual private server. Here is a list of the main technologies we used. I won't go through all of them, but the most important are probably AWS and Vercel that we use for hosting, and then Slicer that we use for the 3D segmentation. So this is 3D Slicer. We use this for the segmentation of the patient scans. It's an open source software that's used throughout the medical industry for viewing scans. You upload your CT MRI scans, and then you can place seeds within an anatomical structure. And from there, you can grow the seeds. And as you can see from the picture on the right, this is kind of an example of a segmentation where each specific body part is segmented.
Right, so this is our workflow for segmentation. First, we load the medical scans, the Nifty files into 3D Slicer. Next, we run the automated segmentation using Total Segmentator, which identifies and labels key anatomical structures. After that, we apply refinement and smoothing, like Gaussian smoothing, and then finally we export it as an STL file. So this talks about Total Segmentator. This automates the segmentation. It identifies over 100 anatomical structures without manual input, and it's trained on 1,000 plus annotated CT scans. It delivers strong anatomical accuracy and generalization.
For our patient database, we use Postgres, and for our scans database, we use Orthonc. In order for the doctors to successfully make the 3D reconstruction, they need to be able to choose the medical scans that the reconstruction is based upon. And these medical scans followed a structured hierarchy where a study represents the complete imaging exam that's performed on a patient. And within a study, there's many series, and a series is a collection of the related images. And lastly, an instance is a single image within a series, which is representing a DICOM file. And the doctors need to be able to go through this efficiently so that they're able to select 3 or more for the 3D reconstruction.
The cannula placement interface lets users position a cannula within a patient's aorta. After loading the aorta model, users can choose 12 different cannulas, 9 with built-in angles and 3 with a default 0-degree angle. Each comes in different size millimeter diameters. A user can rotate, zoom, adjust placement manually or with sliders. And once positioned, the model is finalized and sent to Blender for processing. For the fluid simulation, the 3D model must be a single watertight mesh to prevent leaks. Our Python script in Blender handles this by combining the user-placed cannula and aorta. The cannula cuts an opening in the aortic wall, and the two models are merged. The script then cleans up messy geometry, fixes gaps, and corrects surface normals to avoid invisible leaks. The final cleaned model is then ready for the simulation.
So, what are the broader impacts of OptiVAD? Our hope is OptiVAD can be used in healthcare all around the country. First and foremost, it will improve LVAD patient outcomes, reducing the risk of complications. We hope it can be a useful tool in helping surgeons visualize and simulate an LVAD implant for their patients before any real surgery would happen. It is an easy-to-use software and most importantly is free. Software such as Mimics, a 3D medical imaging segmentation software, can cost thousands of dollars. We believe that life-saving technology shouldn't be hidden behind a paywall. This is the first iteration of this software, and we're hopeful it can be developed even further, from more types of implants to developing a neural network for future possible uses, not just segmentation. With enough data, we believe this software would be able to place the cannula and LVAD in what would be the ideal implant before any simulation is run. We are excited to see where this software will go in the future.
Right now, we're going to go through a quick demo. Okay, so this is our web app. So first, a user will sign in. From there, it pulls up the patients that are in the LVAD system. So a user will add these patients if they're going through heart failure or waiting for heart transplant. And we can view these scans for these patients. So these are the studies for that patient because they have their own accession number. And we could view the series from that study. So these are all the series for that study. They have what body part they're from, if they're an MRI or a CT scan. And we can also sort by the number of instances. So we could view the series here in the actual instances. A user can click through them and see which ones they want to send to get segmented. And they need to pick 3 in order for the segmentation to work, process them, and then it loads the hemodynamic data that a user previously inputted. From there, we could start it. And then once it goes through the segmentation, it will create a simulation for that patient. We could view the aorta that was just segmented. And then if it looks good, they could go to the cannula placement page. From there, they could load the aorta. And this takes a couple seconds to load into. So once it loads the aorta, a user could add a cannula to the image, and they could place the cannula where they want it. So once they like the placement, we can press the upload placement button, and that'll mesh the 2 models together to create one STL file. And this takes a couple seconds to mesh it and make sure it's all watertight. And then once it works, we get a download button, and we could download that final model, and then it gets downloaded to the user's computer where they could go and upload it to the fluid dynamics simulation. So that is our quick demo. Thank you for listening.